Lesson 3.3 deals with piece functions, or piecewise function they're often called. They're just functions that come in pieces. They require two or more function rules to define them, and each rule applies to a restricted interval or piece of the domain. And so what we're going to have is we're going to have a different function for a specific part of the domain. We see this happening in real life when you buy things in bulk. Let's say you go to a place where you can buy t-shirts, and if you buy from 1 to 5 t-shirts, it's going to cost you maybe $12 per t-shirt. So that's $12 per t-shirt, which means if you bought 2 t-shirts, it would be $24. If you bought 3 t-shirts, it would be $36. But then if you buy more than 5, they might only charge you $10 per t-shirt. And then maybe they'll say from 11 to 20, it will be $9 per t-shirt. And maybe anything 20 plus, you're going to pay $8 per t-shirt. So this would be a piecewise function, and it actually tells you the cost. So this would be 12x if x is between 1 and 5. You take $12 times the number of t-shirts. But if you buy from 6 to 10, you're only paying 10x. So there's an example of a piecewise function that actually occurs in real life. The ones that we'll be looking at won't be as practical, but the same idea holds true. So first of all, it's just saying evaluate a few values. So f of 0. What we need to do here is we need to figure out in what piece of my function does 0 fall. And here we see that f of x equals 4x squared if x is less than or equal to 0. So f of 0, x is equal to 0, so we want to put it in that first function. So we have 4 times 0 squared, which is just 0. And then f of 7, we want to see where 7 lies in our domain. So is 7 less than or equal to 0? It's not, so 7 doesn't lie in there. Looking at the next part, is 7 greater than 0? Yes, it is, so we want to plug 7 into that piece or part of the function. So we put in 7, 2 times 7 plus 3 is 17. All right, this next one, we'll slide this over and make it bigger, so we're going to graph this. This top part means really we're just graphing, and you don't have to write this each time, but we're graphing y equals 1/2 x plus 2. And the second part, we're graphing y equals x squared. But there is an interval that we're going to graph those things on. So this first part, this line in green, y equals 1/2 x plus 2, we only want to graph when x is less than -1. So sometimes what we can do is we can think of that vertical line, x is less than -1. So here's x is 1. We want this green graph to the left of that, or less than that. So we're going to graph y equals 1/2 x plus 2. So the y-intercept is 2. The slope is 1/2. So we could go up 1, right 2. Or what would be more helpful to us would be to go down 1, left 2, because we want this graph to the left here. And so instead of graphing the whole line, I only want to go up to that x equals -1. We put a circle there, and then we decide what we want to do with the circle. Do we fill it in, or do we leave it open? We can determine that by that inequality. It does not have the or equal to, so we want to leave it open. Also, we want to go ahead and erase these points because they're not part of our function. Now we're going to graph this other piece, this light blue piece. This is y equals x squared. Well, we know by now what y equals x squared looks like. It's a parabola. It goes through 0, 0, 1, 1. If we put a 2 in there, 2 squared is 4, 3 squared is 9. And then same thing on the other side. And so we graph that parabola, and we only graph it when x is greater than or equal to -1. Well, we do have an equal to there, so we do want to fill that in. So those two graphs together make that piecewise function. There are a few special types of piecewise functions that we're going to look at today. The first one's called the greatest integer function. Each y value is the greatest integer less than or equal to the given x value. So you want the highest integer without going over the number that you're referring to. So whatever number's in there, you want the highest integer or greatest integer that's less than or equal to that. I like to think of this as the always round down. Just a practical way of thinking of it. Always round down function. The domain is the real numbers. And the range, if we're always rounding down to the nearest integer, the range is just going to be the integers. So the reason we study this in this lesson is because it is a piece function. Looking at our interval, let's actually start with this one. Anything from 1 to 2, so like 1, 1.1, 1.15, 1.37, 1.58, 1.95, all of these, anything between 1 and 2, we always round down. So if we put these in our brackets, all of these will just round down to 1. So when x is between 1 and 2, it rounds down to 1. If x is between 0 and 1, so all of these equal 1. Between 0 and 1, they'll always round down to 0. And so actually we're going to go ahead and jump to this example of graphing this. So as we just mentioned, between 1 and 2, between these two places on the graph, that will always round down to 1. So it's going to look like that. Anything between 0 and 1 rounds down to 0. That's an open circle. Anything between 1 and 2 and 3, 2.1, 2.3, 2.4, whatever those x values is, they'll round down to 2, so our y value would be 2. And that pattern continues, so the graph of the general piecewise function looks like this. And just like the other functions, this can be shifted left or right or up or down, and it can be made more steep or less steep. Over here, we're going to go back, now that we have that graphed. Oh, also notice the domain is the real numbers, the whole x-axis is covered, and the range is just the integers. We mentioned that before. So find the set of ordered pairs described by the greatest integer function, and the domain is -4, -2.2, -0.5, 0, 6.8, and 2.9. So let's go ahead and find the set of ordered pairs. So if we do f of -4, well, that is an integer, it just is -4. So that ordered pair is -4, -4. F of -2.2, this is where it sometimes gets tricky, but if you think of a number line, here's 0, -1, -2, -3. -2.2 is right about there, and remember, we want to round down. We want the greatest integer less than or equal to that number, so it rounds down to -3. So we have the point -2.2, -3. Next one, -0.5. Once again, we're in this negative range, so here's -0.5. That's going to round down to -1. So the negatives sometimes are tricky. F of 0, well, that is an integer, so it's just equal to itself. So we have the point 0, 0. One looks like a 4 kind of, so that was -1. F of 0.68, we want to round that down to the nearest integer, so 0.68 rounds down to 0. And the last one, F of 2.9, even though it's really close to 3, we still round down. And so we have the 0.2, 2.9, sorry, 2.9, 2. What was I doing up here? This one before, I switched those. That's, the x value was 0.68, and the y value is 0. There we go. So there is the set of ordered pairs. So the greatest integer function is actually a piecewise function. We always round down. You should be familiar with the graph of that, and you should be able to plug into a function. Next, the absolute value function. This one should be familiar to you. The absolute value function, all values, all points x, f of x, or xy, such that f of x equals the absolute value of x. So a lot of times we think of just always change to a positive. We've also discussed this definition before, but the absolute value function can be written as a piece function. If the absolute value, if this number is greater than 0, so 0 or positive, what I like to say is the absolute value equals itself. But if this number is less than 0 or negative, it's equal to its opposite. So it can be written as a piece function. So what we could do, we can do this two different ways. So we could use this to graph it. Y equals x. Well, y equals mx plus b, the slope is 0. Sorry, the y-intercept is 0 and the slope is 1. And we want that, so we're graphing y equals x when x is greater than or equal to 0. So we want that to the right of 0. So there's the y-axis is x is 0. We want to graph that over here. That's the orange part, purple part. And then over here, we want to graph y equals -x for x is less than 0. So -x has a y-intercept of 0 and a slope of -1. So y equals -x looks like that. So the purple closes this circle, but since they both meet at the same point, there is the graph of the absolute value function. So that's one way to graph it, is to look at that piecewise function. We also could have just done absolute value, -3, 3. The absolute value of -2 is 2. Absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. And 3 is 3. And you see all those points on there. So we need to know by memory that the absolute value function looks like this, v. In the past, when graphing parabolas and some other things, we learned that we can transform a function, and we know that if you add or subtract something inside the function, in this case inside the absolute value, that is going to move it left if the number is positive, if you're adding a positive number in there, and right if it's negative. And that's because you're moving it to the value that makes this whole absolute value 0. On the outside, this moves the function up if positive, and it moves it down if negative. And then out front here, it flips it if it's negative. And then it also changes the slope. So it has two things that it does. flips if negative, not is negative, and changes the slope. So here's our normal absolute value function. This is not the answer. I'm just putting it on here. You don't need to do this. But I'm going to show you the comparison. And let's graph this at h of x in green. So it is going to be moved left 3. Left 3. It's going to be up 1. So we can go ahead and graph our new vertex. So left 3 and up 1. The vertex will be there. It's going to be facing opening downward because it's negative. And then to be more specific, it's going to have the slope of 2 or negative 2 on each side. So we're going to go down to right 1. And down to left 1. So there is the graph of h of x equals negative 2 times the absolute value of x plus 3 plus 1.